Okay, last little limits thing here. This is we'll have some kind of review at the end, but this is the last bit of new material. We're going to try to get it done in one. So we talked about what it means to do a limit at infinity last time, and we got into that big calculator thing and that conceptual stuff. But now it's just going to be practical how to. All these first questions you saw last year. So you could pause it and see if you can answer these questions about what do these things get closer and closer to, if anything, as x goes to infinity. Pause it. Okay, so I hope you tried it just to say, well, what do I remember? Just so that way when I give you the answer, then you go, oh, like you understand, oh, what this I understood and this I didn't understand. Like it helps you know what your misconceptions are so that you can correct them, and then you totally have it down. Okay, the first one, what you want to think of is, the numerator is infinitely big and the denominator is infinitely big, but the denominator is infinitely big squared. So if you have like 5 billion over a billion squared, a billion times a billion, that's going to be a tiny, tiny little number. And so this one's going to be 0. The second one, the numerator's got the squared and the denominator isn't so big. Looking at if x was an infinitely big positive number, because notice x isn't approaching negative infinity, it's approaching positive infinity. So if x is a billion or something, this is going to end up being an answer of negative infinity, because it's going to be a negative numerator and then a positive denominator, but the numerator is going to be huge. So that's why that. And the last one, so it's going to be 4 billion and 3 over a billion, or 4 trillion and 3 over a trillion. And basically you can just ignore this plus 3 because it's going to become inconsequential as x goes to infinity. And so the limit on this is 4. The big thing you should have learned last year is you just look at the exponents. So if it's a smaller number over a bigger number, then as x goes to infinity, remember this is only as x is infinitely big, then it's basically going to be 0, like a bigger exponent, I should say. And bigger over smaller, it's going to be infinity. I guess I can say plus or minus. You have to think that through, decide which one it is. And if it's equal powers, then it's the ratio of the leading coefficients. So that's why this one was 4, because it's 4 over 1. Okay? But you should be able to extend this idea of just thinking about infinitely big things over infinitely small things, or over normal things, or whatever. You just think about that idea in order to work out other problems. So like take this one here, it's sine 2x over x. Now, if we were back in our earlier stuff, as x goes to 0, that limit's equal to 2, because it's 2x over 1x, and the sign doesn't matter because the ratio. We did that a couple lessons ago. But this one, it's x is a number that's getting infinitely big. So if you think about that numerator is just going to be a number between -1 and 1, and the denominator is going to get really, really big. So I don't have to do any algebra here. I can just think it through and go, well, that's got to be 0, because it's going to be a number oscillating between -1 and 1, and then over huge. And so that'll be 0. So you go to the second one, well, the numerator is an x to the 1, and the denominator, now I can't distribute that exponent, but basically this plus 1 over time as x gets infinitely big is not going to really matter. And so I can think of it as x to the x squared to the 1/3. So this expression here is approximately equal to x over x to the 2/3. The plus 1 in the numerator and the plus 1 in the denominator, as x gets infinitely big, are not going to affect what that ratio is very much. And the bigger x gets, then the less the plus 1s affect anything. And so the plus 1s are not really important. Now, you're not really canceling these out, but you're using, like, you can't just algebraically just go, I don't like you, and make it go away. But you could say that this expression here is approximately equal to this, and so therefore the limit is going to be infinity, because the numerator is going to be bigger than the denominator, and as x gets a trillion, a trillion divided by a trillion to the 2/3 is going to be a pretty big number. It's going to be a trillion to the 1/3, whatever the cube root of a trillion is, and then you keep getting bigger after that. Same idea on this one. It's an infinitely big number minus, plus or minus something between -1 and 1. So it's going to oscillate around that really big number. And the denominator is going to be that same big number. This is going to be a ratio. This ratio is going to be 1, right? Because that minus cosine x is not going to matter much. All right. And so ultimately, if as x goes to infinity or negative infinity, you've already seen what I've done. You just have to think, okay, x is a really big number, and then figure out what you think the answer is. So I'm gonna pause for a moment, where I encourage you to pause it and try these ones out. These are all just kind of think it through sort of problems, and I'll give you the answers to all of them. Actually, I think I'm going to pause it and then I'll write them all out. Okay, here are the answers. So this first one, you think x is infinitely big. So you've got this, let me blow this up a little bit, it makes it a little easier. So you've got e to the negative huge number. And so when you're taking a number, when you see e, you're going to see e a lot this year. But just think a number around 3. It's 2.7, 1828, 1828, and then it wanders after that. So 3 to the negative a billion. That's 1 over, e. I'll put that e to the negative, I'll just say 1,000 because I don't feel like writing that many zeros, is equal to 1 over e to the 1,000th, which is basically equal to 0. It's almost 0. Right? And so when you've got that e to that negative number, that's going to make a number that's incredibly close to 0. And so, but you still have the 2 that's sitting here. That doesn't go away. That's not adding to 0 or anything. So the answer would be 1/2. This part here goes to 0. Okay, that was that. I won't have to write too much more. The second one, the idea you think to yourself is, okay, if x is negative infinity, then this e to the negative x is going to be a huge number, e to the infinity, e to the billion. And so therefore it's going to be 2 plus 2. That's going to be a huge denominator. And so the answer is going to be 0. You have 1 over something enormous, and 1 over enormous equals 0. Don't write that down on the AP because they won't take that for credit. But that's the way you think about it so that you can, sort of intuitively grasp what's going on. Next one, I thought, okay, it's a billion. The absolute value doesn't do anything because x is positive. So it's a billion over a billion 1, and that's about 1. And so you notice I'm not doing anything with the absolute value. I'm just thinking it through. And the next one, plug in negative a billion. The numerator would still be a billion, but now the denominator would be negative 999,999,999, I think. That would be basically negative 1. Almost the same numbers, a little bit off, but it would be negative. Now, the last one's getting to this idea of comparing polynomials to exponentials to factorials, because we're going to see factorials not much in the beginning of the year, but later on they're going to be pretty huge. So what happens if x is infinitely big on that first one? So you think, like, what if I had a billion to the 10th? Oh my gosh, that's a huge number, right? But if you have 2 to the billionth power, if you have a billion 2s all multiplying each other, that's going to be a lot bigger. Exponentials get bigger. So that one I deliberately made on this one on the left here. I deliberately made the. You can move. Thank you. Wow, that's as much as you want to move. Okay, but I deliberately made the exponent there 10. Like, whoa, x to the 10th. That's huge. But when x goes to infinity, a billion to the 10th. 2 to the billionth is going to be bigger. And so an exponential function always is going to overcome a polynomial as long as x is going to infinity. And you don't have a negative exponent or something. Basic idea, basic polynomials and exponentials. Yeah, I didn't have to say that technically, but just so nobody's trying to think of an exception, or something. And then you think about the second one, and you got x to the 10th. Whoa, all right, that's huge. Or even if we had 2 to the x in the numerator, well, that's huge. But in the denominator, we have x factorial. So if you think about it, like if x is 1,000, the numerator is 1,000 to the 10th, 1,000, 10 times. The denominator is 1,000 times 999 times 998 times 997 times 996 times 995. Oh my gosh, that's a lot of numbers. That totally will overwhelm your calculator. If I do 100 math factorial overflow, it's too big. But if I do 100, wait, was that 100? Let me see, what was that I tried to type? Yeah, I did 100 factorial, and if I do 100 to the 10th, I get 1 times 10 to the 20th, right? Because it's 10 squared. Sorry, motorcycle. It sounds like. So factorials just get huge as x goes to infinity there, and therefore you could just kind of think of this idea. I know the writing was really terrible there. That like as n goes to infinity, then I guess I should say n since I said n there. Want to be accurate, right? Factorials are bigger than exponentials or bigger than polynomials. I mean, n factorial is bigger than 10 to the n is bigger than n to the 10th. Okay, so that's just a general rule that can help you to simplify working out some of these problems. All right, and now that's to review. So that is chapter 1. We'll have some suggested problems for you to do. Hope you work through these, and then also some suggested problems so you can practice if you want. We'll have a review that covers the whole chapter, so you can make sure that you're feeling confident about it. And that's the chapter 1 stuff. Again, we're not going to have a test on this. We're not going to have an assessment that you have to do. It's going to be graded or something. This is going to be based on completion of the practice test that I'm going to give you, which is basically going to be like a altered form of the test last year. So you'll be able to check in, make sure that you got the information. Almost all this stuff you should have seen last year. There's probably just a few little things, especially the continuity thing, squeeze theorem, intermediate value theorem. Those were a little weird. And maybe some of the like little detaily things, like that x goes to infinity thing and what we mean by that, and like, the whole idea of what closer and closer means. That was kind of interesting, but you can see it's just like little fill-ins. Okay. That's it. That's chapter 1. And we'll be posting some practice problems and the practice tests and stuff so that you have a chance to make sure that you feel confident about this material. Let me know if you have any questions. Email me. And thanks a lot for doing this, because if you're successful, I'm happy. So I appreciate it. Thanks.